3 servers. 1 user click. Which right is truth when the network lies? Distributed systems cannot share one memory, so they must agree on a log of decisions. If they disagree, you get split brain, 2 leaders, 2 truths, corrupted money and corrupted configs. Clients may see success on one side and failure on the other. Debugging becomes archaeology. Paxos is the classic theory of consensus. It is powerful and famously hard to teach. Raft is designed so working engineers can understand, implement, and operate consensus safely. In this video you will build a durable mental model of Raft, leaders, terms, elections, log replication, and commits. We will kill the wrong intuition of a single forever primary, then walk the protocol step by step. By the end you can redraw election and replication, explain majority quorums, and answer system design questions without hand-waving. This knowledge sits under Append, Consul, and many Kubernetes control plane components. Treat it as infrastructure literacy, not trivia. The naive fix is, appoint a primary and let it decide everything. That works in the happy path until the primary freezes, the network partitions, or 2 primaries both believe they are in charge. Clients may write to the wrong side and read stale or divergent state. You have not built a distributed system. You have built a single point of failure with extra latency. Heartbeat alone is not enough. You need rules that prevent 2 leaders for the same term, and rules that stop an outdated node from overwriting newer committed history after it reconnects. Raft solves this with terms as logical clocks, majority votes, and a strictly ordered replicated log. Consensus is not about making every node the fastest. It is about making the cluster safe under failure. If you only optimize for happy path latency, you will learn safety the expensive way in production. Keep that tension visible. Availability goals always trade against consistency when the network splits. Good engineers name the trade-off before they name the library. Raft has 3 roles. Followers passively accept log entries from a leader and respond to heartbeats. A candidate runs for election when it times out waiting for those heartbeats. A leader handles client requests and replicates the log to followers. Only one leader should be active for a given term under normal operation. Time is divided into terms. Each term is numbered and increases monotonically. Each term has at most 1 leader. Terms act like logical clocks. Higher term always wins arguments about who is current. If a node sees a higher term in a message, it updates its term and steps down to follower. That single rule kills zombie leaders after partitions heal. Heartbeats from the leader reset follower election timers so stable leadership stays stable. If heartbeats stop long enough, followers start elections. Randomized election timeouts reduce split votes where no candidate gets a majority. Remember the triad: leader for client simplicity, majority for safety, terms for freshness. Election flow in detail. A follower times out, increments its current term, becomes a candidate, and votes for itself. It sends request vote messages to peers including its last log index and term. A peer grants a vote only if the candidate's log is at least as up to date as its own, and only if it has not already voted for another candidate in that same term. 1 vote per term per node. That discipline matters. Majority wins. That majority is the quorum. In a cluster of 5, 3 votes elect a leader. In a cluster of 3, 2 votes elect a leader. Why majority? Any 2 majorities must overlap in at least 1 node. Therefore 2 different leaders cannot both commit conflicting histories for the same term without sharing a witness. If the vote splits 3 ways, no one wins. Candidates time out, bump the term, and try again with fresh random delays. Once elected, the leader sends heartbeats immediately so others stop campaigning. Interview signal, explain quorum intersection and log up-to-date checks, not just they vote for a leader. After election, clients send writes to the leader. The leader appends a command as a new log entry, then sends append entries RPCs to followers. Each log entry carries an index and a term stamp. Followers append only if the previous index and term match what they already have. That consistency check keeps log prefixes identical across healthy nodes. If a follower is behind or has diverged after a crash, the leader reduces the next index and walks backward until the prefixes match, then ships the missing suffix. Log repair is normal, not exotic. An entry becomes committed when the leader knows it is stored on a majority of servers. Then the leader applies it to the state machine and can acknowledge the client. Followers apply committed entries as they learn the leader's commit index through later messages. Critical nuance: committed means majority durable, not that every slow replica already has the bytes. That is how Raft provides strong agreement without waiting for the last unhealthy node. The latency of a commit roughly tracks the slower members of the majority, which is why cluster sizing and placement matter. Safety rules are the product customers actually buy when they buy consensus. Raft guarantees that once a log entry is committed, no future leader will omit it or replace it with a different command at that index. Election restriction enforces this: candidates with outdated logs cannot win leadership. A stale node returning from a long partition cannot delete committed history just because it still feels important. Leaders also follow careful commit rules across term boundaries so partial replication does not become silent data loss. When a leader crashes mid-flight, a new election occurs. Clients retry. Designing idempotent commands makes those retries safe. When a follower crashes, the leader keeps retrying append entries until catch-up completes. Under a network partition, the minority side lacks quorum, so it cannot elect a leader or commit new entries. The majority side can continue. That is CAP in operational clothing. During partition, progress requires choosing the majority. If your product cannot accept that, you need a different consistency model, not a broken Raft. In system design interviews, draw roles, terms, and the log before you name it or a cloud service. Boxes and arrows beat buzzwords. Say, 1 leader per term, elections by majority vote, replication with previous index matching, commit when a majority has the entry. Call out trade-offs without being asked. Strong leadership simplifies clients and reasoning, but the leader can become a throughput hotspot. Reads can be served carefully. Naive follower reads may be stale unless you use leader leases or read index techniques. Compare briefly to multi-leader or eventually consistent stores when the product can tolerate divergence for higher availability. Mention real systems. Append and Consul use Raft for strongly consistent metadata and coordination. If asked Raft versus Paxos, answer: same problem, class agreement under failure, with Raft optimized for understandability and practical implementation. Seniors narrate failure modes, split votes, log repair, minority partitions, leader storms. That storytelling is the higher signal. Recap the mental model. Distributed systems need agreement under failure, not hope. Raft uses a leader for client simplicity, terms as logical clocks, majority quorums for elections and commits, and a matched replicated log so histories do not silently fork. Committed entries stay committed. Stale candidates cannot erase them. Minority partitions cannot invent a second truth. If you can redraw election, replication, and safety from memory, you understand Raft well enough to discuss it in design reviews. Exercise: simulate 3 nodes on paper. Kill the leader after only 1 follower acknowledged a right. Decide who becomes leader next and whether the client should see success. For more systems mental models in 30 seconds, follow CodeSnap 30. Subscribe for the next deep dive, and share this with anyone prepping distributed system design interviews. See you in the next one.